Okay, so we're ready to talk about some basic examples of finding the area between two curves. So let's just get started. It's highly useful when you're doing these problems to try to draw a picture of what's happening. So when I write an example down, I'm immediately going to plot the functions that I see in the example because that's going to guide how I approach using the formula that we came up with in the lecture. So example 1 here is the following. So I want to find the area between y is equal to x squared plus 1, y is equal to x is equal to 0, and x is equal to 1. Before I do any calculus, I'm going to draw a picture and make sure I understand what the situation looks like. So there's my coordinate axis. Here's where you get to test how strong your pre-calculus knowledge is. The graph of x squared plus 1 is a parabola. It opens upward, and its y-intercept is at 1. So it looks like this. The line y equals x is a line. Intercept 0, slope 1. Finally, I'm going to put the bounds of my region in. So the bounds of my region are x is equal to 0, which I already have here, and x is equal to 1, which I will put right here. Now, when I'm chopping this region up, I have to decide which way the rectangles are going to go. Are they going to be up and down rectangles, or are they going to be left and right rectangles? That's the difference between a dx integral and a dy integral. I make that decision based on where the curves are. I want the curves to be the top and bottom of the rectangle, and sometimes I don't have a choice about how that's going to work. So I'm going to draw a typical rectangle and see what that looks like. So a typical rectangle here, I think, should look like this. And I can draw it as a rectangle because, remember, it's just an approximation. Okay? So typical rectangle is going to look like this. I know immediately that because it's oriented in this direction, that the height of this rectangle should be f of x minus g of x, wherever that rectangle happens to be located. And the width of the rectangle, well, it's skinny in the x direction, which means its width should be delta x. So the area of a typical rectangle is going to be f of x minus g of x delta x. That's going to guide how I build this formula. So let's look more specifically at the computation that we're going to need. So I'm going to draw this again. So this is example 1 continued. I know that my typical rectangle looks like this. It's delta x wide. It's f of x minus g of x tall. Okay? And I know that the region that I'm looking at is supposed to be like this, and I'm cutting it up into lots and lots and lots of these rectangles. Even without knowing the formula, right? So I don't like to approach calculus from the idea of memorizing formulas. I like to try to build the formulas out of the situation that I'm looking at. You don't have to do it this way, but this is the way I'm going to approach these problems. I know that I'm taking these rectangles and I'm taking this region and I'm chopping it up into lots of rectangles this way. And the first rectangle is located at x equals 0, and the last rectangle is located at x equals 1. So this is x equals 0, and this is equal to x equals 1. And I'm going to add all of those rectangles up. So I know that I'm looking at an integral that starts at 0 and ends at 1, because the first rectangle was at 0, and I chop and chop and chop until I get to x equals 1. And the height of the, and this is where I get to use this formula right here. My typical rectangle was f of x minus g of x tall and delta x wide, which means I'm looking at f of x minus g of x tall times dx wide in the integral. Okay? Well, now I just get to use my regular old integration techniques. So the integral in this particular case turns into the integral from 0 to 1 of x squared plus 1 minus x dx. Okay, so now let's actually do the integral. So the integral from 0 to 1 of x squared plus 1, remember that's f, minus x dx. So this was a, this is b, this is f of x, this is g of x, this is the dx in the formula. This is equal to the integral from 0 to 1 of x squared minus x plus 1 dx. I like to write my integrals in descending order. So now I'm going to use the power rule. At the beginning of the class, I'm going to try to remind you some of the basic rules you were supposed to come into the class already in possession of. So the integral of x to the n dx is x to the n plus 1 over n plus 1, as long as n is not equal to negative 1. So I apply the power rule to get x to the third over 3 minus x squared over 2 plus x evaluated from 0 to 1. When you plug this in, 1/3 minus 1/2 plus 1, you end up with 5/6. Okay? Now, does your answer make sense? Well, yes. Areas under curves are always positive. So areas between curves are always positive. Okay? All right, example 2. So let's look at a problem that says find the area between y equals x squared and y is equal to 2x minus x squared. Now notice this time that I didn't get limits of integration, so I'm going to have to find where these curves intersect with each other in order to figure out a description of the region that I'm interested in. So, plot. Well, let's see. So we have y is equal to x squared is a parabola that opens upwards. Y is equal to 2x minus x squared, so here's a trick, is x times 2 minus x. So that's a downward opening parabola with x-intercepts at 0 and 2. It's downward opening, of course, because there's a negative sign in front of the x squared. What I'm doing here is I'm saying, well, this is equal to 0. This is equal to 0 when x is equal to 0, or when 2 minus x is equal to 0. So this parabola must have x-intercepts 0 when x is 0, and also 0 when x is equal to 2. So the negative makes it open downward. These give me the intercepts. So this is sort of a cheap way of drawing a parabola. Hopefully you can draw one more symmetric than that. Okay, so that's a sketch of what my region should be. I can think now, how do I want to cut this up? Well, there's some things I need to know. I know that I'm going to start cutting at x equals 0. And wherever that point is right there is where I'm going to stop making rectangles. To be consistent here, I want to choose rectangles that open up and down. And the reason that I want them to open up and down is because I want the tops and the bottoms of the rectangles to stay the same, determined by the same curves. So I'm going to think about taking this region and cutting it up in this direction. Okay? And so the first thing, okay, so that's the first thing. As I'm choosing the rectangles, well, I choose vertical rectangles. The second thing is to figure out where the beginning and end of this region are. It's obvious from the graph that they both cross at 0. So I'm going to find the points of intersection. So it's obvious that they both cross at 0. I'm going to check that with algebra anyway. The way that you calculate intersection points between curves is you set them equal to each other. So x squared is equal to 2x minus x squared. Solving this into a quadratic gets me 2x squared minus 2x is equal to 0. The 0 property then says, after you factor, that x times x minus 1 is equal to 0. Those are the roots of that particular algebraic equation, which means the intersection points of these curves are x equals 0 and x is equal to 1. Okay, so that point right there happens at x is equal to 1. Now you notice I don't need to be terribly accurate about the way that my plot is on the page, because that's actually the vertex of the red parabola. So my graph is inaccurate, but the graph is supposed to guide your thinking about where the rectangles are and to tell you what things you need to find. So in this particular case, where those points of intersections are. Okay, so this is going to be the beginning and end of my rectangle. So how do we actually compute this? So let me resketch it real quick. The situation that we're looking at was we had a parabola that opened downward. We have a parabola that opens upward. We're thinking about rectangles as being up here. So a typical rectangle for this problem is going to look like delta x wide. On the top, the curve is given by, well, it's the downward parabola. So the top of this is given by f of x is equal to 2x minus x squared. The bottom curve is the blue curve of that particular rectangle. So the bottom of the rectangle is given by g of x is equal to x squared. And so the height of the rectangle is going to be 2x minus x squared minus x squared. Top minus bottom. Okay? So the typical area is going to be given by 2x minus 2x squared. That's the height of each rectangle times delta x. Well, once I have my typical rectangle and I know where the beginning and ending of my integration is, I just have the formula there right in front of me. I want to add up rectangles that start at 0 and end at 1, and the area of each rectangle I'm adding is this, which means I just know that the formula for this has to be the integral from 0 to 1, because remember, they start at 0, they intersect at 1, which defines the bounds of the region. And then I'm adding up all the rectangles inside, 2x minus 2x squared dx. Again, without memorizing a formula, I can intuit what this formula should be from a plot and understanding the basic intuition of calculus, which is that we think of infinitesimal approximations and then add. Okay, so the last thing to do is just compute the integral. So if I have the area is equal to the integral from 0 to 1 of 2x minus 2x squared dx, again, by the power rule, this is x squared minus 2x to the third over 3. And I'm going to evaluate that from 0 to 1. If I plug in the 1 here, I get 1 minus 2/3, which is 1/3. And that's the end of the problem. Okay, so the next set of examples are going to be in the next video, are going to talk about what happens when the region that we're interested in has places where the curves switch position. So f is on top for a while, and then they flip places and f is on bottom. So look for that next.